In this video, I want to talk about delta to Y or pi to T equivalent circuits. So, if you remember, before we talked about the Wheatstone bridge. So what happens if we replace the galvanometer with its equivalent resistance? Here I call it Rm. And we redraw the circuit. How can we analyze this circuit now? Right? So right now what we have is that the R3 is not variable anymore. So it means that we cannot change this to the point for which the current in the middle branch to be 0. So because of the interconnection of this circuit, the circuit cannot be easily simplified to its equivalent resistance. Remember, we said that if we have resistance in series, we can easily find the equivalent resistance by summing all the resistance. Or if we have resistors in parallel, we can use their appropriate equation. 1 over Req was equal to 1 over R1 plus 1 over R2 all the way to 1 over Rn, right? We could use that to find the equivalent resistance. But for this circuit, as you can see, R1 and R2 are not parallel. They don't share a pair of nodes. Or they are not in series either, right? Because this node, which is shared between R1 and R2, is also connected to this DC voltage source, right? The same is true for the other ones as well. So R2, Rm, and Rx are not neither in series nor in parallel, right? So because of that, it is not as simple to find the equivalent resistance for this circuit. So for us to simplify this circuit, we need to come up with a little bit more complex conversions. So here I talk about delta to Y and also pi to T conversions. One thing that you should have in mind is that delta to Y or pi to T are practically the same things. So let's just think about these two circuits. We have nodes A, B, and C for the left circuit, and also we have node A, B, and C. Basically all these dots here, they are all node C because they are all connected to the same point and there is no element in between them. So if you look closely, you see that these two circuits are practically the same. So even though this one is shaped like a triangle and this one is shaped like a square, right? They are practically the same thing. We have RC between node A and B. The same is here. We have RB between node A and C. And also we have RA between node B and C, right? So this one, since it's like a triangle or the Greek letter delta, we call it a delta interconnection. This one, since it's similar to pi, we call it a pi interconnection. But they are practically the same circuit. So let's just take a look at these two other circuits. We have again node A, B, and C for both of them. We have node A, we have resistor 1 to be connected between node A and this node. I can call it D, for example. We have resistor 2 to be connected between node B and D. And finally, we have resistor 3 to be connected between node C and D. Let's just take a look at this second one. We have A, B, and C, and let's just call this D. So as you can see, these two configurations are also identical because we have R1 between node A and node D, R2 between node B and node D, and R3 between node C and node D. So since this one looks like a Y we call it the Y configuration, and since this one looks like a T, we call it the T configuration. So the delta and the pi configurations are exactly the same, or practically the same. The same is true for Y and T configurations. So these ones are the same. So that's why we either say delta to Y conversion or pi to T conversion, right? Or you can even say delta to T conversion or pi to Y conversion. It doesn't make any difference. So now that this is out of the way, let's just see what we can do for our circuit now. How can we convert between these two types of circuits? So we have this configuration, this delta configuration with resistors RC, RB, and RA. RC is between nodes A and B, RA is between node B and C, and RB is between node A and C. So I named these with subscript A, B, C. For the T configuration, we have the same nodes A, B, and C. But now we have this additional node D, and we have R1 between A and D, R2 between B and D, and R3 between C and D. So for these resistors, I chose a numbering convention. So for the first one, I use RA, RB, and RC. For these ones, I use R1, R2, and R3. So what we want to do is that we want to find the relationship between RA, RB, and RC, and R1, R2, and R3 in such a way that these two circuits are completely equivalent. So if these two were in a box and you only had access to node A, node B, and node C, if some relationship exists between RA, RB, and RC, and also R1, R2, and R3, you cannot tell the difference only by looking at the terminals, right? So that is what I mean by the equivalent, they be equivalent circuits. So let's just go through steps and see what are the relationship between these resistors. So this is a rephrase of what I just said. So equivalent circuit means that the terminal behavior of the delta configuration is identical to that of the Y configuration. In other words, in each circuit, if each circuit is placed in a black box, it is not possible to tell which configuration is in which box by external measurement. So these two circuits are identical only if the resistance between the corresponding terminal pairs is the same for all of the terminal pairs. So we have terminal A, terminal B, and terminal C. So what is the resistance between terminal A and B? So I call it RAB. Or what is the resistance between terminal B and C? I call it RBC. Or what is the resistance between terminal A and C? I call it RAC. So between these two circuits, if the resistance between terminal A and B for the delta configuration is the same as the resistance between terminal A and B for the Y configuration, also, if the resistance between terminal A and C in the delta configuration the same as the resistance between terminal A and C in the Y configuration, also if the resistance between terminal B and C in the delta configuration is the same as the resistance between terminal B and C in the Y configuration, if this is satisfied, then we can say these two are completely equivalent. So I can write it like this. So I just say delta y here. So if the RAB of delta is equal to RAB of y, and if RAC of delta equal to RAC of y, and if RBC of delta is equal to RBC of y, if all these conditions are satisfied, so all must be true. If all of them are satisfied, that means that these two circuits are completely equivalent. So let's just see what are the conditions for all these conditions to be satisfied. So if we are looking at these two terminals, right? And let's just assume that C is up in the air, it's not connected anywhere. What do we see? So from this point, we see that we have our C in parallel with the series of RA and RB. So if C is not connected anywhere, we have here RA plus RB being in parallel to RC. So the way that I can show it is RAB for the delta is RC in parallel to RA plus RB. So let's just do the same thing for the Y configuration or the T configuration. If C is not connected anywhere, what is the resistance that we see between terminal A and terminal B for the Y configuration? So our AB for the Y configuration, since C is not connected anywhere, that means that this path is open circuit. So no current would go through it. So for our intention and purposes, this is open circuit, so it looks as if R3 is not there anymore. So our AB for the Y configuration is going to be R1 plus R2. You can do the same for the other ones as well. So for example, for RBC, for the delta configuration, the resistance that we see from between B and C nodes, while A is not connected anywhere. So since A is not connected anywhere, RC and RB are in series, and the result is in parallel with RA. So it will be RA in parallel with RB plus RC. What about for RBC for the Y or T configuration? When A is not connected anywhere, that means that it is open circuit, there is no current going through it. So for all intents and purposes, this is open circuit, so it looks as if R1 is not even there anymore. So this will be R2 plus R3. And finally, let's just do the same for RAC. For RAC of the delta configuration, the resistance that we see between these two nodes, when B is not connected anywhere, we have RB to be in parallel with RA plus RC. What about for the Y or T configuration? So RAC for the Y configuration, since B is not connected anywhere, that means that R2 is open circuit, no current would go through it. So for all intentions and purposes, R2 is not there. So it will be R1 plus R3. So we said that these two circuits are identical only if the resistance between corresponding terminal pairs is the same for all of the terminal pairs. So for them to be identical, RAB of the delta circuit needs to be equal to RAB of the Y circuit. RBC of the delta circuit needs to be equal to RBC of the Y circuit, and RAC of the delta circuit needs to be identical to RAC of the Y circuit. So now that we have this, we can easily find the values for R1, R2, or R3 based on RA, RB, or RC, or vice versa. Find the values for RA, RB, RC based on the values of R1, R2, and R3. Because no matter from which side we look at this, it is going to be a 3 by 3 linear system. So you should know how this thing can be done. So as I was saying, all the calculations that we did got reduced to these three equations, which basically show the resistance between terminal A and B for both of them, which needs to be equal, the resistance between terminal B and C, and the resistance between terminal C and A. So if you do the algebraic manipulations of the equations, this is the result that you get. So I'm not going to go over the detail. You can refer to the book or do the calculations on your own. But if we do this, we get these three equations for the values of R1, R2, and R3. So what does it mean? It means that if you have this circuit in the delta configuration with values RA, RB, and RC known, right? Using these three equations, you can convert this circuit into a Y configuration. And for each one of these R1, R2, and R3s, you can calculate their corresponding values. So the values that you calculate using these three equations would create a separate circuit which for all intentions and purposes is equivalent to the first one. Why? Because again, the conditions at which we drive these equations was that the resistance between each terminal, between the three terminal pairs that we can have, are equal for both of these circuits. So that one was for the delta to Y conversion. The same can be done for Y to delta conversion. So if you do the algebraic manipulation, this is the equivalent circuit that you can have. So if you have a Y circuit with values of resistors being R1, R2, and R3, you can easily plug these numbers into these three equations to find the equivalent resistance for RA, RB, and RC. And when you do that, you basically converted your Y configuration into a delta configuration. So in this video, we learn how we can convert from a delta to Y configuration or from a pi to T configuration. And this can be very useful in the cases that, for example, for the Wheatstone bridge, we, instead of the galvanometer at the central branch, we have an additional resistor. So that helps us to simplify that equation and get to an equivalent circuit which can be easily simplified, and you can find the equivalent resistance with much more ease.